In this two-part tutorial, we will provide an introduction to the ROS file system, and we will end the tutorial after we implement basic ROS code and visualize some data. This follows the ROS Indigo installation on Ubuntu 14.04. The organizational hierarchy in ROS can be described with three broad layers. The lower end of the hierarchy is the node. Nodes are programs and scripts, your C++ or Python code. Most of the times, a collection of nodes are required to implement some larger goal. These nodes are kept in the middle layer of the hierarchy, called a ROS package. A collection of packages is kept in a container called the workspace, the topmost layer of the hierarchy. Think of this setup in terms of our lab. The workspace will be the lab itself. A package can be a particular action like drinking coffee or printing, and each package will contain related executables like a cup, coffee machine, or A4 size paper. We will now go through each layer, familiarizing ourselves with few useful ROS commands and tools. Make sure you have the ROS environment sourced. This essentially means that the location of the installed ROS components is stored in your environment. This lets you access installed ROS components from anywhere in your system. We begin by creating a workspace. In your home folder, execute these three commands. Catkin is a ROS tool for compiling the different subsystems and modules used in ROS. Like CMake, but over a larger scale, and it's specifically designed keeping in mind some ROS requirements. Perform a Catkin make from the root of the workspace. The devel and build folders at the root of the workspace are where the linked libraries and the compiled code in machine language resides. Source the environment using source devel setup.bash. We will now create a package. In the src folder, type in the command catkin create package, beginner tutorials, standard messages, rospy, roscpp. The beginner tutorials is the name of the package, and the standard messages, rospy, roscpp, are dependencies that we are defining. Use catkin_make from the root of the workspace. Source and confirm if your workspace is indeed added to your current environment by doing. We will now use the roscd command to access a package within a workspace. If the environment containing the package is sourced, we should be able to navigate to that package by using the roscd package name. Here we can verify this by using roscd begin_tutorial. We will now work with the LIDAR to demonstrate other aspects of the ROS file system. Plug in the URG04LX and make sure you see the green light on the LIDAR indicating power. We are now going to install some ROS binaries that will help us use the LIDAR. ROS has a vast library of packages, and these can be downloaded either as binaries or source code. Use the sudo apt get install ROS Indigo HKOU node command in a terminal. To be able to access the LIDAR, we should change the permissions of the TTY ACM0 port. Do this by using the chmod command. Ensure that the LIDAR is indeed at port TTY ACM0 and not at ACM1. roscd into the HKOU node. This takes us directly into the downloaded package of the HKOU node. Opt ROS Indigo share is the location where all the binaries are downloaded. Now, if you have sourced your environment, you should be able to roscd into beginner_tutorials directly. This is the advantage of roscd. We will now initiate the ROS framework by running the command roscore in the terminal. It's the master that communicates with all ROS subsystems and provides an interconnect among them. It needs to be running in the background before any ROS code can be launched. It's like the clock in any microcontroller. Once we have roscore running in another terminal or tab, we run the HKOU node by running rosrun HKOU_node HKOU_node. ROSrun is used to run any executable in a particular package. Here, the name of a package and the executable are the same. Once the node is initiated, we can examine the data that is being published by the LIDAR. A node publishes its data on channels called topics. These topics are predefined in code and carry data of the defined data type. We use ROS methods like ROS topic list, echo, info to examine topics and related entities. Here, when we do a ROS topic list, we see scan topic that is active. ROS out is the topic that is active the moment you start ROS core. It is responsible for logging ROS events and messages. On performing ROS topic info scan, we see the node that is responsible for publishing this topic. We also see that the message type that this topic carries is the laser scan data type. This data type is provided for in the standard_messages library we had initially included. We can view the raw data that is being published on this topic by performing ROS topic echo scan. The data values you see are the distances as measured by the LIDAR to objects around it. So we now have a Hokuyu node publishing data of type laser scan on the scan topic. The different nodes in the ROS system communicate with each other through such topics. ROS provides us excellent visualization tools as well. In a new terminal, type in ROS run rviz. Once rviz is open, in the field frame name, type in laser. Click on the add button to add the topic that is to be visualized. You will see on rviz the laser scan as published by the LIDAR. Another tool that ROS provides us is the Rqt Graph Tool. In another terminal, type in ROS run Rqt Graph. This tool shows us the various topics and nodes that are active and how they are communicating with each other. Right now, there's only one node publishing a topic. In the second part of this tutorial, we will implement a node that listens to the scan and process it for a particular application. Please go through the description for important link and FAQs.